1, chapter 14. Pen here. And this will be on heat. All right. And calorimetry. All right, so this is chapter 14. We've talked about energy before. Again, when we have kinetic energy is 1/2 mv squared. This is in units of joules. And we have potential energy, mgh, and again, this is units of joules. So, in this case, we're using heat, and when we're talking about heat, we're used to, the idea of calorie, right? If you look at, again, the video on absolute zero, they talk about the calorie. The term actually comes from the term caloric, which was thought to be an actual substance, so that, and this was developed by Antoine Lavoisier, who was a very famous French chemist, who was actually one of the originators of modern chemistry. Unfortunately, he died during the French Revolution. And he came up with this idea of caloric, because what happened is when you heat ice, or cool ice, you take water and freeze it to ice, it would expand as it turned into a solid. Again, this is one of the characteristics unique to water, is the sense that it expands when it freezes, unlike other substances. So Lavoisier had thought that this expansion was due to the fact that caloric was added to the substance, the water. And so somehow this idea of caloric as being a real element, coming and going from materials, was a hard thing to get rid of. What was realized is, instead of things being added to it to make it solid, it was just that the molecules were getting farther apart. And the way this was done, if you look at the video, is by weighing a block, a kilogram of water, and then freeze it, and you weigh it again. Well, it still weighs a kilogram. It's not adding any more heat to it, it just expands. So this idea of caloric became eventually calorie, and so this is our unit of heat. And it's defined as 1 calorie is equal to 4.186 joules. And this was actually done by James Joule, when he realized, what he was able to do is by taking, say, some water or something and having it fall a certain distance, right? When it fell and hit there, it would gain temperature. So it had a rise in temperature based on the amount of mass, what we call the specific heat. So when it changed, it would change into heat. When it hit the ground, it would rise slightly because of the collision with the ground. And so we have mechanical energy. So this is what we call mechanical energy. And it's shown to be equivalent to heat energy. All right? And so this is, how we convert it to, in the relationship between calories and joules. We could use, they're both interchangeable. It's just a mechanical energy, which you're generally using joules, for heat energy reason calories. So that's the relationship. We'll keep that up. 1 calorie, 4.186 joules. So keep that in mind. All right, so we're going to go on to the next part. Then, all right, internal energy. All right, when we talk, we'll do this more. Internal energy. Let's say of a gas. We have a gas. The internal energy in it is given by 3/2 nRT, where T is the gas constant. Okay. We'll be using this more in chapter 15 for next semester. Then this is number of moles. This is the gas constant. And this is the temperature in degrees Kelvin. Okay, so we'll be using this later, but this will be more for chapter 15 when we get into this concept. All right, so keep this in mind for later on. So, specific heat. All right, specific heat is given by letter C, and what this means is that this is units of calories per gram degrees Celsius. And what this means is that when we add heat, we're going to use the letter Q for heat. So this will be heat in calories. All right. We get into later on entropy and stuff. We get into chapter 15 next semester. We'll be using joules, but for here, MC, change in temperature, where this is the mass in grams. This is in the units of calories per gram, and this is in degrees Celsius. It's degrees Celsius, degrees Kelvin. It doesn't make any difference. Now, what's nice, the reason we do this in calories is water, H2O, has a C of 1 calorie per gram degrees Celsius. Right? So it's the standard. That's kind of how it ended up being defined, is it takes 1 calorie to raise 1 gram of water 1 degree Celsius. So everything is related to that. So we got other materials, like iron, Fe is C is 0.22. Metals are usually very small. Silver is C is 0.056, and so on. And so metals are very small as far as this is concerned. So this is water, and this is primarily what we're going to be dealing with here, is just with mixtures of water as far as that's concerned. All right, so let's do an example of this with water. Okay. So water, and so generally, so if I take, let's say 500 grams or 50 grams of water, and raise it from 20 degrees Celsius up to 50 degrees Celsius. What is Q? Well, Q is MC delta T, so it'd be 50 times 1 times a change in temperature, which is 30. That would be 1,500 calories, right? So that's what we have there, 1,500 calories. So that's the expression we'll be using for here, as far as that's concerned. All right, let's do another one. All right, we'll get into temperature mixing now. And we do a quick one here, and then I'll move on to the concept of latent heat. So say I have 100 grams H2O at 0 degrees Celsius, and I have 50 grams of water at 30 degrees Celsius. All right, mix them together. So I put them together, so I got twice as much here. All right, now you would think, logically, and this is true, that the final temperature should be somewhere between, now this is the freezing point of water and very warm water, somewhere in between. So how do we calculate precisely what? Well, the way I do it is I do heat loss, Q loss equals Q gain. All right? So this is going to lose heat, this is going to gain heat. So how do we do that? Again, our expression is Q is MC delta T. So we're going to have is, this will be 1 and 2. Just calling them that way. So Q loss will be, we have M2 times 1 times the change in temperature. So it's going to go from 30 degrees down to some final temperature, right? So it's going to drop, so it's going to lose heat. On the other hand, M1 times 1 is going to gain heat, and it's going to have a final temperature of 0 for that. And then what we want to do is just solve for T final. Well, this is 50 times 1 is 50 times 30 minus T final equals 100 times T final minus 0. So that's 1,500 minus 50 TF equals 100 TF minus 0. Okay, add 50 TF to both sides. 1,500 equals 150 TF. And therefore our final temperature is 10 degrees Celsius, which makes sense because we got twice as much. So that's our final temperature there. Okay. So that's our final temp, all right? So this is how I do heat gain. So I do it as the one that's losing heat because this becomes a positive number, and the one that's gaining heat, I put T final front because that's gaining heat, all right? So that seems to work. And if I had a couple things, I could add them together. If I had a third one, which is, I could put it anywhere I want, any way I want, as long as you do that. So that's what we have there, all right? So let's move on to the next part. And again, we got our Q is MC delta T. Now we're going to go into the concept of latent heat. And I'll just show this graph here. And the concept of latent heat is based on the fact that you heat, let's say you have water at 0 degrees in blue, 0 degrees, you heat it until it all melts, right? Then once it melts, the temperature starts to rise until it becomes steam, and then it stays again. So this concept of you have because this is also called what they call hidden heat, is from ice to water, or the other way around, and water to steam. While the water is melting, ice is melting, the temperature is not rising. When water boils and turns into steam, the temperature is not rising. This is again, it's at 0 degrees Celsius, and this is 100 degrees Celsius. So we end up with this concept of what we call latent heat, and this is Q for here is M times the latent heat of fusion from ice to water, and this is Q is mass times latent heat of vaporization. Notice there's no temperature involved here, it's just the mass times that. Now LF is 80 calories per gram. LV is 540 calories per gram. And this was discovered really by James Watt when they were trying to develop steam engines, realizing that there is a tremendous amount of heat in steam, tremendous amount. You know, you take 1 calorie of steam and convert it back to water, it gives off 540 calories, right? That is a huge amount of energy. Again, remember, specific heat of water is 1. So again, this is water. So there's tremendous amount. It's why steam is so dangerous. Because if you get steam on you, that heat, it condenses immediately to water, releases that heat, some goes out, a lot of it goes in your skin and burns you. So that's the thing there. Also why ice can take so long to melt. You know, big lake, because it takes a long time for that energy to turn from ice to water. All right, so let's do a quick example here. And then I got a mixture problem. Then we'll do one last one. And what we have here is say we have 100 calories, 100 grams of ice at 0 degrees Celsius. Then how much does it take to melt? Energy to melt, well, it would be Q would be 100 times 80, 8,000 calories. All right? Okay. Let's do a quick example here related to this. All right, so we did the first problem, we did water, mixing water. Now we're gonna let's say we take 100 grams of ice at 0 degrees Celsius. You can have it below, but it's easier just to do it there. And we take 100 grams of water at 100 degrees. So right at the boiling point. Okay. And we figure out what is the final temperature. All right. So what we got to do now, we got heat loss. So heat loss, right? So heat loss equals heat gain. And what we have here is heat loss. We'll have MC delta T, and this is 1 and 2, so it'll be 1 equals heat gain. Oh, T2 M1C delta T plus we first have to melt it. Okay. So this will be 100 times 1 times 100 minus T final. And then this will be equal to 100, because they're both the same, times 1 times T final minus 0 plus 100 times 80, right? So this turns out to be 10,000 minus 100 TF. This is 100 TF plus 8,000. All right, because 100 times 0, 0. All right, so subtract 8,000 from this side, that's 2,000 plus 100 to both sides is 200 T. So the final temperature is 10 degrees Celsius. Okay, that's our final. All right, let's change this problem slightly, right? So instead of we have 100 grams of water, let's say at 100 degrees Celsius, let's say we start at, room temperature 20 degrees Celsius. And we mix that with water, ice. All right. Same thing. So we got heat loss equals heat gain. So to simplify, redoing the numbers, the right side will be exactly the same. The left side, the only thing different, if you look at it, what's the only thing that's going to be different? We still have the same mass, still the same specific heat, but the only thing that's different is we're starting at a different initial temperature. So we have 20. The right side is still the same. So now I'll fix this and go from here. So what do we have here? This is 2,000 minus 100 TF equals 100 TF plus 8,000. Subtract 8,000 from both sides. Add 200 T, 100 T, I should say. This is minus 6,000 equals 200 TF. Divide by 200 on both sides, and we get a temperature final of minus 30 degrees Celsius. All right, so this is what the math leads to. All right, of course this makes no sense. I mean, you mix ice at 0 with water at 20, it's not going to end up below, 30 degrees below Celsius degree. I mean, that's like super cold. It's like temperature in Bemidji in the winter. What's happened? Well, what we didn't realize is that there's not enough heat in here to melt all the ice. What we actually end up with, rather than that, we end up the temperature final is 0 degrees Celsius, but it's an ice plus water mixture. In reality, what it means is we only will melt about a quarter of the water, because there's 2,000 calories in the water to give up, even if it goes all the way to 0, right? And it takes 8,000 calories, so it'll only melt about 25%, so it's going to be about 75% ice, 25% water. And again, it's an indication of how much energy it takes to actually do that. So that's an example there. You gotta be careful what your answers give you, because this assumes all the ice is, it's just not working. So that's you gotta be careful what your result means, not just do it as a math problem, end up it that way, and go from there. Okay, last section here, we'll just talk briefly about 3 types of radiation. We'll do this a lot. We'll do this later on when we get more into heat. So I'm just going to get into this roughly, and particularly when we get into other parts later on. All right, so heat transfer. This is again the last part, and this will be more on the concept base, except for when we talk about radiation. So we have conduction, right? Transfer by molecular vibration, right? So you have a solid, you take solid, hot, cold. The heat transfers solely by vibrating molecules, cools this side off, heats that side up. Convection, by transfer by movement of molecules. So like a boiling pot, you heat the bottom, the hot water goes up, the cold water sinks because it's denser, and you get a convection cycle going. This is how the atmosphere heats. It's up because we have gravity, that when you heat, hotter water is less dense than colder water, so the hot water is going to rise, the cold water is going to sink, and this is exactly how weather works. And then the last thing is radiation. And that is by electromagnetic process. So basically a hot object. And the way this actually works is by Q, heat this way is given as what we call the Stefan-Boltzmann, a constant times T to the 4th. Meaning, and this is in degrees Kelvin, and what this means is the amount of energy transfer goes as the 4th power. So if we have energy at 100 degrees, so if we radiate, say, at 100 degrees Kelvin, 1,000 watts of energy, power. At 200 degrees, it's going to be 2 to the 4th, or 16,000 watts of power. So it goes as the 4th power. If you were to triple it, it would be 3 to the 4th. So this is very temperature dependent as far as that's concerned. It's a process of how we get energy from the sun, works in a vacuum. So we'll, again, deal with this more later when we talk about black body radiation and stuff, but that's not part of this chapter at the moment. Okay, we'll get into that later as far as that's concerned. Okay. And that's okay. So that is chapter 14, and we'll go from there. All right. So I have the review from last. So we have the review that'll be posted for the exam 12, exam 5, which will be on chapters 12, 13, and 14, which will open on December 1st. Okay.